Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, good afternoon. Welcome to the first afternoon session of the first day. This is going to be the first session where we have our RFP winners present some of their work. And this session is focusing on photographs, a lot of photos, especially laid out in various contexts for geography. The first two talks will talk about matching photos with either existing databases of photos or with a 3D environment. And the first talk will be by Kristen, who is currently at University of Texas at Austin. And even though MIT doesn't appear on their intro slide, a lot of this work was initially conceived of while Trevor was still at MIT. I'll let Kristen go ahead.
Can you hear me through here? Okay. Well, good afternoon. I'm really excited to be here to give this talk and also to meet a lot of you and talk about any intersecting areas that we share, and it seems to be there's a lot of them. So yeah, this work is done by myself and two students at UT Austin, Pratik Jain and Brian Kulis, and some portion of it also done with Trevor Darrell. And I want you to consider this general problem of wanting to be able to do location recognition with an image-based search. So this can be kind of the scenario to imagine why the techniques we're developing are going to be useful. So you take a picture with your mobile device, you send it to a system that's going to tell you where you are based on what you're looking at. So what are the technical challenges here? Well, we're going to have to do this indexing on a very large-scale database. So we'll come in with this image and look through some large repository like the Virtual Earth collection and try to find out what's relevant so we can return it. So there's certainly a complexity issue. There's also the robustness issue because the person taking this photo presumably could have completely variable viewpoint relative to the scene that they're looking at, and this gets down to the real core challenges in the recognition task itself, trying to deal with this real variability to provide the most robustness. So what I wanted to talk about today are some of our work on building sublinear time indexing techniques for what I'm calling good image metrics. So not necessarily the ones that are easy to define, but the ones that we know are going to be very valuable for comparing images. So these sublinear time search methods, the basic idea is we want to come right in and immediately isolate, without doing any computation besides an initial hash, those examples that are likely to be relevant for the query. Okay. And I'm going to talk today about two different directions in this project. One is how to do a fast search within such a large set of images when you care about the correspondences between a bunch of local features in the image. The second, I'll talk about how then, if you actually learn a metric that you want to apply to do your search, how you can still guarantee a fast index on top of that. Okay. So in terms of robustness, we know of some good and reliable features that are local that will give us robustness even in the face of a lot of the variations you see here. So here are extreme examples where object pose or occlusions are really changing the images that we capture. And so certainly in the global sense, we know that these images are so different, we won't see a strong similarity. But if we look at local portions within them, there's going to be some repeated parts. And that's the basic idea of a lot of techniques today that are using local feature representations for recognition purposes. I'm showing just a collection of options you have for these local features. Some are specifically designed to be invariant to things like scale, rotation, translation. Some will capture shape, appearance, so on. But in general, they give you ways to decompose the entire image into parts that can be useful and that you can describe in invariant ways. Okay. So what would be a useful thing to do once you have an image that you're describing in all these local pieces? One good thing to do is try to see how well each one of those pieces matches up with some piece in another image. Because if I have a good one-to-one correspondence between all these local parts, then that suggests a good agreement overall in the objects within the images. So that's a point set matching problem. we want to know the least cost matching between two sets of possibly high-dimensional points. And that, to compute optimally, meaning to really minimize the cost between the things that you pair up, costs cubic time in the number of points within one of the images. So in previous work, we had shown a linear time approximation for that matching, which means you can have very large sets of these features and still efficiently compute such a correspondence distance measure. Okay, so I'm going to give an intuition about the general approach behind that approximation, because then I'm going to tell you how to go a step further and not just compare two images under the match, but actually take a large database and search it when what you care about is that correspondence matching. So here's the core of this idea, which is to quantize your feature space, and I'll show you it's going to be at different resolutions, but to quantize it so that you can easily read off the number of possible matches at that given resolution. So to do this, we're going to look at the intersection between two histograms, and the intersection is the sum of the minimum counts within every bin of two histograms. So what we have are these point sets where every point comes from some patch feature, and so this could be a SIF descriptor or some other kind of local point in the image, and we want to get that matching between the two. Well, if I look at some partitioning of the feature space, and then I intersect the histograms, so I'm looking at the minimum counts in each, that count actually reveals implicitly how many matches are possible at that resolution. So here we have an overlap of 3, or an intersection value of 3, and implicitly that means there's possibly 3 matches that could be formed. Okay, so the pyramid match, which is our approximate algorithm, then does this at multiple scales. And this is scale within whatever feature space you're using. So starting from the fine resolution, we'll have some number of intersections. There'll be few because this is these are very small bins with which we can match. So we'll record how many points are matching based on the intersection, and then start making these bins larger and larger, so more and more points are now going to be intersecting, and we'll keep counting them. And in fact, we'll subtract off counts that we've seen before. So the basic image is that by using this multi-resolution partition of the feature space, you can efficiently, and in linear time in the number of points, read off how many matches are possible as you increase distance. Okay. So the pyramid match then gives us this approximate measure. The optimal matching entirely could be slightly different in terms of the one-to-one correspondence, but the cost is what we're getting that's approximately, and we have bounds for this, is going to give you what you would have gotten with the optimal measure. Okay, so now the new problem is if I have this image that I've described with local patches of some kind, and I have a huge database of images described the same way, then I don't want to search through every single one, even with my efficient matching process. I want to find in some sublinear time those examples that have the highest matching similarity. So in other words, it's the indexing task, but now the metric that we care about is this one-to-one partial correspondence between points. So how can we do this in sublinear time so that I only address a few of these n examples? So the basic idea we have is to try and take these point sets and map a single point set to some vector embedding, where that embedded space is going to guarantee that an easier to compute distance, it's going to be a dot product, will give me an approximation of the original matching score. Okay? So remember, every input that we have is a list of vectors, those point descriptors, and I'm indexing in with them all together to find the match. So we're going to develop an embedding function that will take such a list of vectors, map it to a single high-dimensional point, where distance against that single high-dimensional point and other such embedded points is the correspondence match that we care about. Once we're able to do this, we may be able to leverage techniques like locality-sensitive hashing. This is an approximate nearest neighbor technique based on the idea that if I have a hash function, h, that guarantees that the probability that two examples, x and y, fall into the same hash bin is equal to the similarity measure that I care about, then I can do a guaranteed sublinear time search with a trade-off between accuracy and the time that I'm willing to spend. So if I have a hash function like this and apply it to all these examples, put them into this hash table, there's a good chance we can guarantee that things are similar, are likely to fall together in the table. And then when we come in with a new query, we're going directly to those examples that are similar to it. Doing that, then I only have to search a very small number of points and compare them to the query and sort them to find the approximate nearest neighbors. So this is a very general technique and very appealing because we'd like to be able to use this general format to guarantee a good search for any interesting measure. However, it's so far defined for metrics like L2, L1, a dot product. And right now what we're trying to do is set our similarity measure to be that correspondence matching. So the important thing to note is we need to be able to design a hash function that maintains this kind of guarantee. And that's what we're providing for the correspondence measure. Okay. So in order to do this, we look at a property of random hyperplanes. And the idea is that if you have two vectors and they have a small angle between them, if you take some random hyperplane that you select uniformly at random in terms of its orientation here, it's likely not to fall between them. If you do the same with vectors that are very distant or that have a low dot product, low inner product, then it's likely that they'll be split. So specifically, if you have these two vectors vi, vj, the red and blue vectors, then the probability that their sign, the sign of their dot product with this random vector, which is the dotted line here, is different, is equal to this expression. So the probability of having the same sign on that dot product depends on how distant these initial red and blue vectors are. So why is this going to be useful for doing this sublinear time search? Well, this property is going to let you design a hash function where you can independently come in with one of your vectors and compute a dot product with some random vector and store it according to the sign, so a 0 or 1 bit. And then next time you come in with a new vector, you do the same thing. And the probability that they fall together or have the same hash bit depends on what their dot product with one another was going to be. And that's this vi.vj. Okay, so that's defining a hash function that'll work for a dot product. But we're not at a dot product yet. We still have this correspondence match that we're trying to handle. So now I'll show you how we can map the correspondence match problem into an inner product. And that's going to let me do that embedding so that I can then hash under the matching. So to do this, we need this property of intersection. So remember that kernel I briefly defined is based on the idea of intersecting histograms. So if I intersect these two histograms, then the min value in each bin, I've got 1, 0, 3. And you can expand that out in a unary kind of coding like this. So if I say, okay, I've got a 1 here, and I'll pad that with some zeros. This one has 3, I've got 3 1s, pad that. Do that all the way out. So that's a vector for representing this entire histogram. And same thing over here, 2, 3, and 0 in the middle. Now, notice that if I then take the inner product of these two unary encodings, I actually get the intersection value itself, which is the sum of those minimums, which is 4 in this case. Okay, so this is then what's going to allow us to make an implicit matching, or implicit mapping from our point sets into these very large vectors, which we could then use this dot product hash function to match. This is the actual definition for the pyramid match kernel, which is that approximate matching function. It goes over L levels of a multi-resolution histogram and counts the number of matches based on the difference in intersection values. And then I can rewrite this, so really it's simply just a weighted sum of intersection values. So that means then I can take a point set, map it to that multi-res histogram in the feature space, but then stack up the items that were in each level of that histogram into a single vector and apply the right weights So on the slide before, I had these subtracted weight terms multiplied by an intersection. So now if I scale these histograms that are concatenated by the right weights in each place, I'm now at the point where a dot product between these implicit unary encodings is going to give me exactly that original pyramid match kernel value. So we started with points at x. We got a histogram. We stacked it up. We weighted it in the right way so that now when I take the inner product between two such encodings, I'm getting the original pyramid match kernel value. And I'm doing all this so that now I can go and use that hash function that's defined for the inner product to do a guaranteed sublinear time search. So the embedding of those 2 point sets, x and y, the inner product is the pyramid match kernel. Okay, so here's our hash function then. It's parameterized by some random vector r. And given one of our embeddings for a point set, that's f of x, it'll return 0 or 1 depending on the sign of the inner product of our embedding with that random vector. So notice this function is independent of any other input. You just take a single input and map it to a hash bit. And now we're guaranteed that the probability that the hash bits are going to be equal for any two sets of points is equal to this expression, which basically is proportional to the pyramid match kernel between the original inputs. Okay. So then completing that picture, now we're able to go and do sublinear time search with a guarantee because we've been able to come up with a function that says the probability of collision in the hash table is equal to the similarity measure that we wanted. And so we'll hash all of these examples into this table, come in with a new query, apply our same hash function, come up with a small set, and get our approximate nearest neighbors. So I'll show you one result with this part of the method, and it's on an object retrieval problem. So the goal is to be able to take an image of an object, find out what it is based on what it's matching to in some collection of images. And this result is using a database of 101 different categories that was developed at Caltech. It's like the images you see here. I'm showing 3 examples from different kinds of categories. And what we do is we extract some local features from all the images. We use a SIFT descriptor, and we densely sample the entire image. And then what we're doing is searching under the matching according to this pyramid match hashing that I just described. So here's a result. We are looking at the error in the classification according to those nearest neighbors that we index to, relative to this parameter that we're allowed to tune, which says how much accuracy we're willing to sacrifice for speed. And this is this epsilon parameter related to locality-sensitive hashing. Basically, the more we go to the right, we're going to search things faster, but we'll have more error. The more we go to the left, we'll search more things, so we'll be slower, but we'll be guaranteed to have lower error. And this error in the straight line is the best one could possibly do, and that's with a linear scan. So if I actually took every input, looked at every other input in the database, and ranked them, the k-nearest neighbor classification error would sit here. Whereas when we do the hashing, we will search a much smaller fraction of the database, and our error will increase with that parameter I just described, but essentially we'll be searching 2% maybe or less of the entire database and still getting accuracy close to that linear scan.
What's the scale on the axis, the error rate? What is that?
Yes, this is percent error in the k-nearest neighbor classification. And this is a 101-way classification. So 1% chance error. Yeah, so right now here we're at 70% error, which is 30% accuracy on the Caltech 101. And this is on nearest neighbor search using that correspondence. If we're to use, if we're actually to learn from this kernel, this would be more like 55% accuracy. Okay, so I just showed you how to do this. We can do this indexing when we care about a set-to-set correspondence. And now I'll talk about some more recent work where we actually want to learn a metric based on some constraints someone's provided and use that learn metric to still guarantee fast search. So for example, we know that not all the time will the appearance in an image reveal what's truly relevant or what's the semantic relationship across examples. I could have a very good correspondence here between these points and some here, but I actually have a really good correspondence here between these leaves, let's say. So which of these similarities are actually relevant? That's something that we might get constraints externally about. So what if someone says, well, all of these in your training examples, these are all relevant to one another, but this one's not. So we want to be able to exploit that information and use it to affect the distance function we use to do the indexing. So to do this, we can turn to metric learning techniques that will take those constraints that were given and remap the feature space essentially so that similar examples fall close together under your distance function, and the ones that are like those that are dissimilar are going to be more distant, even despite the fact that what you actually measured could have made it as similar to these others. There are a number of techniques to do metric learning and kernel learning, and many of them allow one to provide these pairwise constraints where you say, these two are similar, these two are not, or A is closer to B than C. And I've listed a number of techniques that can be employed to do the actual learning of the metric. But what we care about then is to now take that metric you've learned and do a fast search on top of it. Well, when you have a specialized distance function, you can't immediately plug into these locality-sensitive hashing methods. And we know that in high-dimensional spaces, exact nearest neighbor search techniques will break down and not be able to provide better than linear scan or time in the worst case. And the functions that have already been defined, like the inner product that we went through or others, do not work for these specialized functions. So our goal, though, is to be able to guarantee you the fast search, but when you're providing some parameterization of a learned metric. And specifically, we'll focus on a Mahalanobis parameterization. The way we accomplish this is to let the parameters of the distance function that you've learned affect how you make that selection of the randomized hash function. So we're going to bias our hash functions according to whatever biases were in the constraints about similarity to similarity that someone gave you ahead of time. So let's look at this in a visual way. Let's say we have these images of, I think, hedgehogs and, well, no, I don't know, beaver and hedgehog, yeah. So I'm a little unsure because these animals in these images look pretty similar. So it'd be quite likely that an image-based metric is going to map them close together. So it'd be useful if someone came and told us, actually, no, these two are similar, these two are different classes, so these are dissimilar. Now the generic hash functions that I mentioned before are going to be selecting these hyperplanes uniformly at random. So this red circle means that we're likely to compute or select any rotation of that hyperplane. We're equally likely. Now instead, if I have this information, I want that to bias that selection. So what we'll do is make a distribution that's going to guide us to be more likely to choose a hyperplane that does not separate those examples that are similar and other examples that are like them. So we're looking at Mahalanobis distances. This is a class of metrics where basically you want to provide some parameters A. This is a D by D matrix for D-dimensional points that's going to give a proper scaling on the points so that essentially we can learn this metric. So generally you might put inverse covariance matrix here, but in fact there's a number of techniques where you can learn this matrix of parameters so that you can better map similar points close to similar points. So this is defined in terms of distance between vectors xi and xj. We can just map that equivalently to the similarity if we look at this product. So x sub I transpose that parameter matrix A times x sub j. So I want to just give a taste of the main idea of how we'll accomplish this biasing of the hash functions. We have this learn metric A, and it's a positive definite matrix. So we can factorize it like this, essentially look at the square root of this matrix G. And now we'll parameterize this hash function not just by some random vector R, but also according to the matrix A. And we're going to put that square root matrix, which we're calling G, into the hash function. So essentially, we'll have that random vector, also those parameters, and x. And you can think of this as the hash function now carrying information about those constraints that you learned. Because if I embed or hash my database points using half or square root of this matrix, then when I come in with another input that's also carrying that square root of the matrix, we take the product, the dot product, now we're getting that full expression that we want, which was this x transpose A x sub j. So now that I fit it into a dot product, I get to go back to this relationship between the inner product and the angle between the vectors. And we'll have the guarantee that the collision is proportional to the similarity under the learned metric. So this is the main idea. The problem is this A matrix could be extremely high dimensional. I mean, if it's manageable, this is exactly what we'll do, and we'll compute this explicitly. But if A is thousands, hundreds, thousands, millions of dimensions, we can't manage it explicitly. So what we've been able to do is develop an implicit update for the hash functions that allow you to never explicitly represent this A matrix. And that likewise means we never explicitly represent this G matrix. So by implicitly, I mean by not having this matrix, we'll still be able to accomplish the function of what that G matrix was doing in the explicit case, but we'll do it by looking only at comparisons between our input and some existing examples that were constrained during the metric learning. So this big equation is basically showing the end result of what we can do implicitly. Over here, we have that R transpose G that we had before in the explicit case, and now this is representing our possibly high-dimensional, very high-dimensional input in the feature space. And over here, we're computing this without ever touching G. And we do it in terms of this matrix of coefficients that's indexed over all our C constrained points, and also comparisons between our new input x and existing inputs xi, and these are among the constrained points. So the main message is here that we can do this hashing when you provide a parameterization of a learned metric, and we can do it whether or not that parameterization is explicitly representable. So this is the plot I showed before, and now I'm going to expand it. This was our accuracy using that matching kernel, whether we did a linear scan or we hashed. And now we see this motion in these numbers. So now I'm showing you linear scan accuracy, or actually error rate, if we are to learn from that kernel. So if someone gives us examples that we match, but also constraints, so we improve our kernel to include those constraints. So now our error rate's going from 70 to under 50% on the 101 class problem. And similarly, we can still provide this hashing in which we have control over errors versus speed, and we're actually coming quite close to linear scan. And in fact, doing this kind of learning on top of kernels, it's not limited to the matching kernel that I described. You can apply this metric learning on top of any existing kernel. So we've done this with the pyramid match kernel, but also another correspondence kernel defined from a group at Berkeley. And what we're able to show is that we're actually improving accuracy on this Caltech 101 relative to all state-of-the-art single kernel metrics. So this is showing you the number of training examples you use per category versus accuracy. And accuracy goes up as you train with more data. These are lots and lots of previous techniques. And here, as we learn on top of this kernel, we improve the accuracy. And similarly for the pyramid match. So right now, this is the best result for a single kernel method. Okay, now finally, I wanted to show you some results using our fast indexing methods for some phototourism data. And we got a nice introduction and exposure to this project. And certainly there's a very large-scale search problem involved, where you have these images with some interesting patches, and you want to go into all your previously seen patches and try to make some kind of match, so you can do that 3D reconstruction. So with our technique then, what we'll allow you to do is take the descriptors you have for these patches and immediately isolate a small portion of the database which you need to search in order to find those that are going to be relevant. So here's a result using our technique both to learn a function that's going to compare these patches and also to do the fast search on top of that learned metric. And what these curves are showing you is the recall rate. So I want a high recall rate, meaning I get, if it's the head of the guy at the Trevi Fountain, I get all other patches having the head of the guy at the Trevi Fountain. And our learned metric does improve the recall rate, as you can see between this initial curve, which is a non-learned metric, and our metric that's learned on top of it. And in addition, what I'm showing in these very nearby curves is accuracy with, again, linear scan, which is pink, and if you do our hashing, which you'll notice is very, very near, which is what we want. We don't want to sacrifice too much accuracy, but we need to be able to guarantee that you're going to search a lot less of the data. Okay, so what I've overviewed today are some of our techniques for fast indexing. This is based on some initial work based on computing matches between local features. But then I showed you how we can do large-scale search in sublinear time on top of a matching, and also how to let you learn a metric and do the search on top of that. And I have some pointers to the relevant papers, but I also hope that I'll get a chance to talk to many of you if you have questions about this work, and so I can hear also about your interesting problems where maybe it could be applicable. Thank you for your attention.
Great. We have time for one question. Anybody? Frank?
So the LSH work, I'm sorry. So locality-sensitive hashing normally uses, k hashes and L hash tables. Is that also what you do, or you just use a single hash?
We're using a single hash table, but we're using k bits. So we'll draw k random vectors to establish k random functions, and then concatenate them to a single hash key. Okay, so far in our experiments, we use a single table, but you could certainly try to improve that by duplicating and just having more tables.
Right, because the papers seem to indicate at least that if you use many more tables, that the performance goes up in terms of k nearest neighbors at least, right?
Yeah, definitely, right. So you can make that, just like with that epsilon parameter, which is giving you speed versus accuracy, the more searching you're willing to do, the more guarantee you have of hitting what you need to hit when you do the hash.
Thank you, Kristen. If anybody has any other questions, please try to catch her during the break. We're going to go on to our next talk, which is going to be given by Johannes Kopf. This is work with Oliver Duysen at University of Constance, and they're going to talk about what you can do when you match an image to a terrain model.
All right. Okay, thank you. So this is about our collaboration with Virtual Earth, and it's called Deep Photo, combining photographs with digital terrain and building models. And actually worked on this together with a whole bunch of people. That is Boris and Oliver from my university, and Billy Chan from Virtual Earth, and Madam Michael from Microsoft Research, and Danny from Tel Aviv University and Jerusalem University. So when you're taking a photograph of a scene, you're essentially capturing all those rays from the outside world that run through the optical center of your camera, and you project them to a flat piece of film. That means you end up with a bunch of pixels where you store the color value for each of these rays, but unfortunately, you lose the depth. And this is kind of a sad thing, because if you would have the depth along with your photo, you could do really nice things to your photo. For example, you could remove haze from the photo, since haze is essentially a function of the depth, right? Or since having depth essentially means that you know about the geometry in your photo, you could relight the photo, approximate what it would look like, when you have a different illumination from a different position. And so applications such as these ones here is what this work is about. Now, unfortunately, inferring depth from a single photo is a really challenging and mostly unsolved computer vision problem. And this is why most previous researchers actually worked on manual painting interfaces that allow you to kind of augment your photo with depth. For example, the classical turn to the picture paper provided means to, or gave the user a method to put a simple spidery mesh on top of your photo to give a hint of the depth. And interestingly, even with these simple depth maps, you can sometimes already create a very compelling 3D navigation experience. And later on, there have been a couple of other papers that provided more sophisticated means to kind of enhance your photo with depth. And there have been even some automatic methods, like the ones by Hoyam et al., which are able, in some simple scenes, to completely automatically infer depth maps for single photos. But in this work, we choose to do a completely different approach. Rather than using computer vision methods or manual editing interfaces, we turned this into a registration problem. And by doing so, we made use of two big trends that exist nowadays. So the first trend is geotagging of photos. So there are already a couple of cameras out there, such as this one here, which have built-in GPS devices. And when you take a photograph with one of these cameras, the photo will be augmented with a tag that stores the location and the orientation of the camera when at the point of time when you shot the photo. And the second trend is the availability of very high resolution and very accurate terrain and building models, such as the ones from Virtual Earth that we use here. And now the idea is to use the location of the photo to precisely register this photo to the models. And when we do this, we obviously get a very accurate depth map here. But it's even more than a depth map, because we have a geometric model. That means we can kind of look behind the things that are visible in our photograph. And also, we get things like these textures from Virtual Earth, which are based on satellite images. And so this work is about a whole bunch of interesting and exciting applications that get enabled by this geo-registration of the photographs. And I'm going to show a couple of implementations of applications ranging from image enhancement to novel view synthesis and information visualization in this talk here. Now, since the emphasis here is clearly on these applications here, I will only talk very briefly about our registration method, which is right now manually. So we used the tool for this that was developed by Billy Chan of Virtual Earth. And so we assume that we know the rough location of our photo. And then we ask the user to specify 4 or more point-to-point correspondences, as you can see here, for example. And so this is enough to solve a system of equations which finally gives us the position, the pose, and the focal length of our photograph. And so this is, for example, the result in this case here. And now a photo is geo-registered, and this kind of automatically allows us to start with the applications. So I'm going to talk first a bit about image enhancement. So I guess you know the situation when you take auto photographs of a well-known landscape or a cityscape, for example. But unfortunately, on that particular day, you had bad weather conditions. You see a lot of haze here, and the lighting is pretty boring. It's taken around noon. There are no shadows in these photographs here. And with our system, as I'm going to show you in a couple of seconds, you can take these photographs and enhance them. For example, by removing the haze or changing the lighting in the photographs. It's a bit dramatized here. So let's start with haze, which is one of the most common defects in auto photography. So haze is due to 2 effects, which are called outscattering and inscattering. And you can really nicely capture them with this analytical model here that I'm going to explain. The first effect, outscattering, means that part of the light that gets emitted or reflected from our object gets lost on its way to the camera. And this is because some of the photons hit air molecules or aerosols and get scattered out of the line of sight. So this kind of reduces the contrast of our scene. And we can model this by so where's the mouse pointer? By simply multiplying our original intensity with this unknown attenuation function, which depends on the distance of the object. The second effect is called inscattering, and this is caused by ambient skylight, which gets scattered into the line of sight. So this causes distant objects to appear brighter. And again, we can simply model this by having an airlight coefficient, where's my mouse pointer here, called A, which we multiply by 1 minus our attenuation function. And now it's pretty clear that if we have good estimates of F and A, then we could easily invert this equation here to kind of get the dehaze intensity of our photo. And one common approach to do this is to assume that we live in a constant atmosphere. And in this case, we can analytically solve this equation, because the attenuation function reduces to an exponential function, which with a single parameter here. But you see that we have some problems here with this approach. First of all, the exponential functions go quickly down to 0, and that means that by inverting them, we get some numerical problems and some pixels to blow up in the background, as you see here. And also, another problem is that this assumption of a constant atmosphere is just not true, because in the real world we have spatially varying air pressure and varying mixtures of aerosols. And you see, no matter how I choose this parameter beta here, there's no setting that works for the whole image at once. And well, of course, you can do things to kind of try to avoid these problems. For example, you could use regularization terms to fight the noise simplification here, or you could try to estimate spatially varying parameters, for example, from multiple images. But luckily, in our scenario, there's a much simpler solution. And so let's see how this works. So here's again our haze model. And now I can rewrite this to put f on the left-hand side. And if we ignore a for now, you see that actually the only unknown that we have here is the dehaze intensity that we want to recover. So we cannot do much here. We don't know this. But now the trick in our system is that we can use, instead of the dehaze intensity, we can use the model textures that are associated with virtual Earth models to get a good estimate of f. So these textures here are based on satellite data and aerial images which are taken from planes. And well, they have all kinds of errors. For example, there are color misalignments. They have low resolution partially, and there are artifacts, there are shadows in them. But still, they're good enough to get a good estimate or a robust estimate of f. And the trick here to avoid suffering from all these artifacts is by averaging the values of the hazy image and the model texture image over a large depth range. And by doing that, and if we simply set a to 1 for now, we can recover these haze curves here for this image here. So this is our attenuation function. And if I apply these curves to this image, I get this result here. And you see that this is an almost perfectly dehazed image. You see that we have really almost glowing colors here, and there's no haze anymore in this image here. And it's done completely automatically. So here's again the original image and the dehazed version. So here's another example of an image taken in Yosemite Valley of Half Dome. So if I apply the automatic dehazing method, I get this result here. And again, the original image and the dehazed image. So sometimes when we apply this automatic method, we experience a slight color shift in the background. And this is because we haven't set the correct air light color. We simply set it to 1. And but it's not a big deal, actually, because in this case, we simply offer the user a standard color picking dialog. And it's only a matter of seconds to find the correct setting of the air light, because you get interactive feedback to that. And this is the final result for this image here. And again, this was the original image. OK, so another cool thing that you can do with these haze curves is you can not only use them to remove haze from your photos, you can also use them to add haze to new objects that you put into your photo. And so here's a simple interface that I prototyped where I can duplicate a building and move it around. And you see on the left-hand side, I put haze on this object. And you see this causes the object to perfectly immerse into the scene. Whereas on the right-hand side, where I don't change the colors of the object, you see it totally sticks out. All right. OK, so another very important aspect of taking an interesting picture is the lighting. And I have to admit, when I go out and take pictures, most of them look like these ones here. So you have, they were taken around noon, and so you have pretty dull lighting, no shadows, and it just looks boring. In contrast, most professional photographers take their photos in the so-called golden hour, which is shortly before sunrise or after sunset. And you get these much more dramatic photos here. And so with our system, we can kind of fake this effect or approximate what our photos would look like at a different time of day. So for example, here, I took this photo again of Yosemite and kind of approximated what it would look like at this romantic, sunset here. And you can even animate this to get an animation like this one here. Okay, so I won't go into all the details here. I will just show you a quick overview of the pipeline for this, this effect here. So we start with our input photo, and the first step is to apply automatic dehazing method to remove all the haze from the photo. And then we modulate the colors with a light map that we have computed for the new sun position. We change the global color tone of the photo and change the sky to one that fits the target time of day. And finally, we add haze back into the photo. And so this is the final result here. And this was the original photo. And I'm not necessarily saying that this is a better photo here. It's just a different one. But maybe this is the photo that I really wanted to capture here on this day. So with this system, you can kind of go creative and create all kinds of effects. So here's another version of this photo here. Here's another example. This is a photo of Lower Manhattan. And here's a relighted version that I created for this photo. And here's another one. So here I added fog to the scene. And another one. And of course, you can also create animations where you move the sun around and circle it around the buildings. Okay, so here's another photo. I like this one because it's this one is a perfect example for a totally boring and dull lighting scene. And with our system, you can turn it into a sunny day or a more dramatic day. Or here's another animation. I created like Miami-style waterfront animation. Okay, let me quickly browse through these ones here. Okay, one last thing I want to say about this is that there's a big difference between relighting a photo and simply putting the virtual Earth models under illumination. So here you see a comparison of the original photo and its relighted version and the virtual Earth models with the virtual Earth textures put under the same illumination. And you hopefully agree with me that this one here looks actually much better here. Has less artifacts. Okay, so that was the image enhancement application. Now I want to quickly talk about two other applications. The first one is novel view synthesis. And this is actually pretty much the standard application that people show you when they're talking about photos with depth. And now the cool thing is with our system, because we have such accurate depth maps, we get almost perfect results here. But with our system, we can do even more interesting things. So one thing we can do is we can use our system to extend the frame of a photograph. So for example, you might have this photo here of Yosemite. And so with our system, we can kind of extend its frame and kind of synthesize or approximate what the photo would look like if we had like a bigger field of view for it. And of course, the cool thing here is that the stuff here is not arbitrary, but it's based on a real-world model that we get from virtual Earth. So what we do here is we use the virtual Earth model to drive a guided synthesis process, where we kind of use the colors from the virtual Earth texture to steer our process. And we do this on a cylindrical domain. That means that we can turn our head in every direction. And we also synthesize it on a layer depth image. So this is a data structure which allows us to represent both the visible and invisible things in our photograph. It means we have also texture for, like, say, a mountain that is obscured by another mountain in the photo. And so here's a video of the system, a live demo of the system. So only the center part of this is the original photo. Everything else is synthetic. And now I can move around, look in all directions. And I can also change the viewpoint. And you see, whenever the texture here on the ground would get too distorted, I'm automatically fading over to the virtual Earth textures. Same thing happens when I move the camera up. And so this kind of allows me to get a better feeling of the geometry that I see in our photo. I can move in and look around and move back out. Okay, so let me use the remaining time to quickly talk about last application. So this is actually a whole bunch of applications about information visualization. So because the geo-registration of the photo gives us the exact per pixel geolocation of every pixel in our photo, we can actually fuse the photo with all kinds of GIS databases that we get off the internet. For example, there are huge databases which have the lat-long coordinates of all kinds of landmarks, like famous buildings, mountains, and so on. There are databases with street networks, and even some Wikipedia articles are tagged with their lat-long coordinates. So we can fuse all these information with our photograph and display it. So and here's a prototype interface that we built for this. So it shows next to the photo a map where we highlight the location of the camera, the location we clicked on, and the viewing frustum of the photo. And in another view mode, we show the depth profile for a horizontal line here. See this line that I'm moving around with the mouse? Here you see the depth profile. So I have to admit, this is a bit more useful for landscape photography. It's a bit, kind of hard to understand what's going on in the city scene here. So here's another interesting thing. So here we overlay a street network over our photo. And we both show it in the top-down view. And we also overlay it with the actual photo. And so we see whenever a street is obscured by a building, we render it semi-transparently. And we also highlight the names of the streets and that are under the mouse position here as I move around. Okay, so this is another cool thing that my fellow student Boris implemented. So all these balls here are actually Wikipedia articles that have associated lat-long coordinates. And so I can display them in the photo, and I can actually browse these articles that are visible in this photo. And I can see where, for example, this building here is in our photo. It's here. So here's another one. So this is these are labels of buildings in our photograph. And as I move the mouse around, it'll always show me the 10 or so closest labels that are visible here in the photograph. All right, so this is the last application. This is kind of an object picking tool. So this is based on the object models that we have in Virtual Earth. It always highlights the full building that is under the mouse position. So you can use this, for example, to select a single building and apply further image processing tasks to it. Okay, so let me sum up what I showed to you today. I showed you a system for combining photographs with digital terrain models by using geo-registration. And I showed you that this enables a whole bunch of interesting applications. For example, I showed you how to remove haze from photos or add haze to new objects, how to relight your photos, and how to expand the field or change the viewpoint or fuse it with GIS data. And actually, all the demos that I showed to you here as videos run interactively on my machine. And so tomorrow in the demo session, I'll be happy to show this to you actually on my computer here. Okay, so let me finish up by talking a bit about future work that we could do in the future. So actually, we believe that the applications that I showed you here represent only kind of the tip of the iceberg. And there are many more interesting things that you could do. For example, you could use these 3D models that we get of Virtual Earth for all kinds of computer vision or image processing tasks. For example, you could potentially use them to reduce noise in your photo or sharpen it, refocus it after capturing the photo, or to recover under or overexposed areas in the photo. And also we think that we only used a small amount of the available GIS data of the internet. For example, there are databases which contain kind of different ground materials. So we could potentially label different things like water, grass, pavements in our photograph, and then in turn use this information to improve other applications, for example, tone manipulation. So another important thing to do is to think about what we can do with multiple images. All these applications that I showed you here use a single image. But we believe that by using multiple images, all these applications could actually gain a lot. For example, with image enhancement, we could use multiple images to learn the illumination of a scene and then transfer this illumination to another photograph showing the same scene. Or, for example, in the novel view synthesis application, we could think of a phototourism-like interface where we use the power of our novel view synthesis technique to provide for better transitions between the images. And finally, with the information visualization application, we could use multiple photographs to transfer user-provided labels between images. Okay, so one thing that I would like to do more in the immediate future is to improve the registration. So right now it's done manually, but I think it should be possible to do this automatically. So you would start from GPS data and then use a feature-based approach to automatically snap the location of the virtual camera to the right position. And I also, so one thing is that right now we're using a rigid registration. That means we sometimes get slight misalignments between our photograph and the models from virtual Earth, and we would like to actually try to snap edges from our model always to high gradients in our photograph to provide better registration. Okay, with that, I would like to thank you all for listening, and if you have any questions, thanks. Anyone? Graham.
How important is it that you don't have strong cast shadows in the original image? And can you simply remove them if you do, or are you mostly using kind of overcast skies that diminish that problem?
Yes, right now we don't do anything to remove shadows from our photograph. You can use existing techniques that do that, but we didn't do it. So yeah.
Hi, I wonder if you've thought about adding dynamic elements that you could get off databases like waves or wind or traffic or pedestrians.
Yeah, traffic is one thing I thought of that's very useful, I think, to show traffic patterns in photographs. Yeah, well, maybe waves also, yeah. Something good too. Okay.
Okay, looks like that's it. Thank you very much.
Thank you.
Let's thank the speaker again. So the next talk, the last talk in the session will be by Frank Delaire at Georgia Tech, and he's going to talk about ongoing work on their 4D cities project.
All right, so I'll be talking about actually city capture in general, which is capturing information about cities from large collections of images. This is work with primarily Grant Schindler is my student, and Irfan Isa is kind of our consultant on the project as well at Georgia Tech. Let me see whether this works. Yeah, so this community's goals is really about capturing reality, right? Capturing from images, aerial images, Flickr, the whole of Flickr, the whole of whatever the Microsoft equivalent is of Flickr. What is it? MSN photo database. I don't know. And integrating all this data in a single consistent geometric model, and then interacting with that model. And prime examples are Virtual Earth, of course, and Google Earth, which have really done, have put this community on the map. Now, literally, that is. I'll talk a little bit more about incorporating time in this whole endeavor. So I'm going to focus on urban capture, because urban capture is really the most that speaks to the imagination of people, right? I mean, many people live in urban environments. They are interested in the history of their cities. So there is lots of applications in urban environments, and that's also why a lot of the effort of Google and Microsoft is actually focused on these urban markets. So there is lots of applications, radically new interfaces like photosynth, like on the previous slide, urban planning, historic preservation, and historic renovating in a historically relevant way, and virtual tourism, and lots of applications. Let's see here. Just to focus our attention, if you just ask for Atlanta and downtown tags on Flickr, you get, these are just the 1600 first images you get. And the question then becomes, okay, how can we stitch this in a into a consistent model. And things like phototourism try to do this automatically, and it's an extremely hard problem, right? So we've tried a couple of things to try and at least localize these images in a model. For example, if you have a model like Google Earth or Virtual Earth, and you have a picture which has some tags associated with it. For example, these are pictures that were taken straight from Flickr, and they were tagged by users as with the names of these buildings. So in this image, there were 3 or 4 tags, and just using those tags, like the GE building or the Canary building, if you have a model of the city, you can actually figure out using visualization techniques or techniques on figuring out what possible viewpoints could you be when somebody tags that image. So there's only a couple of places where you can see, for example, the GE building and the Canary building at the same time. So you could at least say, well, it must be taken from around this part of the city, or it must be taken from around this part of the city. So it's a very rough localization that can at least help you in the same way as Kristen, try and get the nearest neighbors as to where you actually could be. So it's a little bit like a hash function, in the sense that you could use those tags to at least put you in the right location. So that's work which doesn't yield a lot of accuracy. So this picture had a number of tags, and we simply sampled from the possible locations in the city where this picture could have been taken, and then resynthesized this image using a very rough model of the city. And if the system works well, then the synthesized images should look a little bit alike the picture. And so you can see that in the top picture, it roughly matches. In the bottom picture, it roughly matches as well. And you can do things like saying, well, pictures are mostly taken from street level or taken from top of buildings, and very rarely are they taken from an airplane, and very rarely are they taken somewhere halfway between a building level and street level, because physically it's very hard to take pictures there. So when we looked at urban environments, we noticed something else, which is we wanted more accuracy than that. So the previous tag-based localization only gives you a very rough estimate as to where you are. And if you want to build 3D models, you kind of want to get closer to where you actually are. So, and we tried throwing wide baseline matching methods to this problem. Wide baseline matching methods are you extract a lot of features from the image. You have a large database where you extracted those features from those images, and you try to index into that database. And so Kristen talked how you could do this efficiently to get at least a recall, where you can then do a more geometrically consistent match. What wide baseline matching methods do not like at all is repeated features. It turns out that if you take a typical image from a typical urban environment, most of the structure here is repeating. So instead of having lots of unique features that you can use for indexing into that database, what you have is the same feature 100 times on this building, the same feature 200 times on that building, and you have to try and match them up. And the typical way of dealing with that is, in fact, throwing them away, saying, oh, this feature occurs a lot in this image. It must be a repeating feature, hence I cannot use it, so I throw it away. Which is, of course, exactly the wrong thing to do if you look at this image, because most of it is repeating. So we thought, well, could we use the repetition to match and index into that database? Whoops, wrong button. There we go. So we submitted something to CVPR, which used that ID, which is we simply extract the repeating patterns from the image, which you can do. There are several papers that tell you how to extract repeating lattices from the images. And then if you have a database, just like what is now available in these interactive 3D environments of textures, you can also do the same lattice extraction from the database of your 3D database, your 3D textures, and then try to match up the lattice in the query image with the lattices in your 3D database. Okay. Now, if you do that, then you get a match, but there is still a little bit of a problem. This match is between a lattice here and a lattice here, and you can match a lattice in many different ways. Okay, and each of these different matches yields a hypothesized camera location in space. Now, luckily, if you have two matches, so you have one building that you match, and you have a family of camera locations, and you match another building with a family of camera locations, you have two grids of possible camera locations, and you can intersect those to find camera locations that are good candidates for the actual location. And so that's exactly what Grant actually did. This is also work in collaboration with Penn State, in fact. Yangxi Liu is an expert on extracting repeated patterns from images, and she helps us a lot in this project. And so if you do that, here's a database of images that we have, buildings that we have. It's a fairly small database. You can see that the blue here is the ground truth position, and the red is our estimated position. And now, instead of being simply in the right block, right, we're at least on the right pavement, and then you can with RANZAC and things you can get it more accurate. Just for illustration purposes, here's a query image with extracted lattices, and here's a synthesized view from that location that we got from that using that technique. So this is all 3D, okay, and this is about trying to use all these images and extracting 3D models from the data. There's a lot of competition in that world, right? The whole Virtual Earth group of Microsoft is in fact trying to compete with us. I'm saying it backwards, of course. We are, in academia, almost running behind the industry. Once a lot of money funnels into, making 3D automatic, it's inevitable that in academia we're going to be struggling to keep up from now on. In fact, so we've been also trying to focus on an aspect that has not been traditionally looked at in this industry that much, although Blaise hinted at it this morning, which is time, right? So all of what I talked about, you can do with 3D. You can also do with historical imagery. And in the 40 Cities project at Georgia Tech, we've been focusing on historical imagery for 4 to 5 years right now, with help from National Science Foundation and also some help from Microsoft Research, where the input images are taken over time. So here's a bunch of images. My laser pointer doesn't work anymore. And some of them are 100 years old. So this image is 100 years old, and these images are just recent images. And some unique problems start popping up if you deal with historical images. Okay, so Grant in CVPR last year presented a paper where we took a bunch of images and assumed that we could do the 3D reconstruction well, which is not actually a given. There is still a lot of work. And then Grant flips the images into their correct time order. So here the idea is you take a bunch of images, you have a 3D reconstruction, try to rearrange the images in the order by which they were taken. And this is something that you cannot do exactly, right? So images that are taken 10 minutes apart, like the images on the back here, cannot be distinguished, right? Because no building went up or was destroyed in the time that the images were taken. And so if you use the 3D structure of the city to order your images, you can only get so far. You can only get a partial order. But you can actually get quite far. Here is an example of this with 20 images. This was presented at CVPR, and I'm not going to go into the detail as to what all these blue and red dots are. In essence, what they are is the constraints about buildings, saying that a building goes up and exists for a while and then goes down. And you make use of those constraints of the urban fabric to order your images in time. And so that's work that's very exciting. By the way, there is, of course, if you use the 3D structure, for every ordering that we recover here, there is also a second ordering immediately, which is by flipping the time axis around. In fact, in Grant's algorithm, he nowhere uses time as a constraint, and so we always have at least two solutions to this problem. Oh, and here I'm supposed to give a live demo. In fact, if you something which Blaise hinted at, and I wanted to call out, I'm going to show it this afternoon. I can show you as a demo here, and Grant tomorrow during the lunch demo session will be available to, let me just restart it, to show you this live, let you interact with the applet. This is something that Grant created really in the last month and a half to show off the results of our research. You see here. So here's a little time animation. This is Atlanta over time. In Atlanta, somebody asked me, wouldn't it be more interesting to take New York or San Francisco as an example of a city instead of Atlanta, which most people, I guess, find not so interesting. But Atlanta is very cool in the sense that if you go back to 1864, there basically was no Atlanta. So, if you know your history, Sherman, who was a Union general, let me hide everything else, came and conquered Atlanta from the south and then proceeded to burn it down. Hence, Atlanta from a research point of view is very interesting because we can start from scratch and see the whole city pop up from 1864. So here's the oldest picture we have, which is by a photographer that came in with Sherman. And now we can go in time. So again, this whole model is built using structure from motion techniques, a la photosynth. So if we go from one image to the next, we actually now see the historical photos in context. We can actually see where they were taken. And so here are some older pictures. In a little bit, here you see the refugees fleeing Atlanta. One of the next, this is the old station. More refugees. All right. Take a look at this building here, which is the station basically where they kept all the trains. Here is Sherman troops bivouacked in the middle of the city, and then pretty soon now they will start destroying things. So this is the same station building, but now destroyed. Okay, and you can get a vivid sense of where all this is taken. If you see these images out of context, you actually don't know where they were taken, right? So, and I never had a visceral connection with these images because I never knew where they were taken. But you can do things like orbit around and now know that that image was taken right here. That still doesn't tell you the whole story. But if I turn on the city as it is now, you can see exactly where that image is in the current modern fabric of time, right? And so with the slider here, I can move time and go and add more and more and more pictures that are taken over time, right? And then I can, if I stop this, I can go to any image here and zoom into it, right? Sorry?
Hit A.
A.
There we go.
Yeah. And just like Johannes, in fact, now we can click on a building. And then what happens is it shows all the images in which this building is visible. So, for example, a building that is not no longer with us, I have to kind of find, so Grant is the demo wizard here, right? So I have to try and find a building that is that was destroyed. So this one is still there. Let me see, go to an older picture here. And what about this one? Yeah, so here you can now see that the range of images is much less than the 200, which is the full database. And this building existed from here to here, where it was demolished. So this is around 1978, and it was built around 1921. So we can go to a 1921 image. Okay, and this is, the red focuses your attention as we're moving between images, right? And shows you where the image is. And again, also because we have the 3D model, the red in this image is a nice, it's not a perfect segmentation because not everything is in the model, but it's almost like a perfect segmentation of the pixels in this image, okay? In a historical context, okay? So we know when each building was demolished and when it was not. Although it turns out that lots of the data on these buildings, on these images, which we get from the Atlanta History Center, are actually wrong. And our model can actually tell, all right, the data on this picture must be wrong because this building wasn't there, etc. So it's interesting that the Atlanta History Center people are sometimes, we had a meeting with them and we told them, okay, this building and this building, or this image and this image is wrongly labeled. So I am not doing this demo justice. Tomorrow, Grant, Demo Wizard, will show this and allow you to interact with it. Let me go back here. So now the part that we've actually been funded for under the RFP, which is another cool idea that came out of Microsoft Research Labs, is these gigapixel panoramas and how to stitch hundreds to thousands of images in a consistent large panorama, which enables a totally different way of interacting with panoramas. Instead of simply going pan and tilt, we now can go deep, and it's almost as adding a different dimension to the images. Okay, and unfortunately, I am running Mac OS on this laptop at the moment, so I can't show you their HD view, but I can show you that the whole community has actually sprung up around the idea of gigapixel panoramas, and people are very motivated to go out, grab panoramas, and share them with the world. And so this is a Carnegie Mellon project called GigaPan, where you can actually interact with these. And I should be online. This is not a particularly good panorama because there is a lot of dynamic structure in the scene. So the mosaicing was really crazy. You can see that there are some privacy issues to these things as well. And in fact, we've put one of these, the idea that we got funded for under the RFP was to put one of these gigapixel sensors in the city with the idea of trying to capture the evolving city as it is changing, right? And the genesis of this idea is because I was driving around. Just like Grant, I always have a camera close to me when I'm driving around in the city, and every time I see something interesting, I try to take the pictures as to not let this moment in time, this sample in space, go away. And I realize it's completely impossible to keep up with the growth of a city like Midtown Atlanta, where skyscrapers are constantly going up and going down, in fact. And so every time I see something new built in Atlanta, I go like, oh, I'm not here with my camera, I can't capture it. So the idea was, well, let's take 100 of these gigapixel sensors and put them all over the city and have them continuously capture the city as it is changing. Okay, so we've made small inroads in this, and this is very much a work in progress. We basically only have a solid semester of work in it, so this is going to be more what could be rather than what is at the moment. But in motivating this project towards my student, I made an analogy between the gigapixel sensor and an eye, right? This is the sensor that we bought is just a commercial off-the-shelf pan-tilt zoom camera, which acts as a server. You can put it on the net and we can grab images from it. And the total field of view is actually unlimited, but here is a 56-degree view on a scene where we stuck the camera. And at the highest zoom level, the field of view is 1 to 2 degrees, which is exactly, in fact, what your eye does, right? You have a very large field of view, almost 180 degrees. In fact, a little more than 180 degrees if you take both eyes, if you can believe that. But the fovea, which is the high-resolution part of your eye, only has a field of view of about 2 degrees. Okay, so you're constantly putting your fovea on different parts of the scene and updating your idea of what the scene is based on what moves, what changes, etc. And we thought that we needed to do this as well because if you put a gigapixel sensor somewhere in an urban fabric and it's mostly almost 98% of the scene is going to be static. What's going to change is the weather, is the 24 modulo cycle there, the shadows, which is a big problem, in fact, when you think about it. And what we want to do is focus our attention on the things that change, right? And simply record those. There is also an interesting problem that we have not tackled yet at all, which is if you capture gigapixel images of the same scene over and over and over, and you do this for, say, 10 years, you probably won't store them as a sequence of simple images. In the compression of storing of these things, you can probably make use of the fact that you're imaging a single scene, right? So eye movement makes perception comprehensive over the scene and intentionally focuses on changing parts of the scene. So the hardware is just a Sony pan-tilt zoom camera. I'm not going to go into this slide. And what we did to try this idea out is we put this camera there. We've been, I think, continuously recording 2 gigapixel a day for about a month. And we take a hierarchical SWAT through the scene. So what we do is, so we do this at multi-resolution. So we take 2 wide-angle shots, then 8 intermediate angle shots, and then say, I think it's 1,000 shots at highest resolution. And here is a little movie of what one of them looks like, right? It's just going all the way across. This is probably level 2 here, or maybe it's already level 3. So probably this is level 3 where, you're very highly focused into the scene, highly zoomed in. Here's a time lapse of the raw imagery, and what you see is that the image is constantly shifting around, right? Because these pan-tilt zoom cameras off the shelf, if you tell them go to this pan-tilt zoom, they don't actually do it. They add some noise to the process. So instead of doing the regular gigapixel where you take all your images and stitch them together, what we want is really a stable base in which to register all the images. So here's a little time lapse of just taking the first image as the base and then registering the other images in there. Let me just show an animation of what is happening. So the first image becomes the base in which the subsequent images are being registered, right? And this is simply using homography matching into the thing. And this is what we continuously do, and updating this mosaic. So what we have to think about is about recursive gigapixel sensor. In a Bayesian framework, what you want is, in fact, you constantly want to update your model. Your model is a gigapixel representation of the scene, given the images at all times, right, which is all your pan-tilt zoom images at every resolution all across the whole of time. And you can do this simply by Bayes' law, right? So here's a posterior on the gigapixel times the likelihood of the current measurement times your predictive density on your model. And then we realized that there is something bad about this. And the bad thing is that M is, because it's a gigapixel image, has 1 million dimensions, times 3 RGB. So this small equation here of Bayes' law turns into something horribly intractable if you try to do anything but the simplest probability model. And so that's what we did. In fact, we used a model for now, which is simply modeling each pixel as independent. And so we have a mean and we have a variance for each image, for each pixel. And as we fit in more and more and more images into the scene, you will see that we're getting more and more confident on some pixels in the scene because we've seen it many, many times. But there's also areas where there is a flag in the image that is constantly changing. And so given our current model of the scene, we see that the flag is not obeying the image model, and we reset all the variances to 0, meaning we have 0 confidence in the pixel at that time. So everything where things are dark, here is a building going up, in fact, is what we see something that is unexpected. Okay, and one of the biggest problems, and I saw some people nodding about the question about shadows. Shadows, of course, always change in the scene, and so we get away by actually taking the panorama always at the same time, roughly the same time during the day. And then this is my last 2 slides because I think I'm going over time. The idea was then, if you have an evolving representation and a density over gigapixel models, then your next measurement should be the measurement that reduces your uncertainty the most. Okay? And just that question is very easily and so it should be argmax, is easily answerable. In theory, we simply want the measurement that is going to maximize the information in our posterior at the next time step. Okay, and this is simply for the next time step. You could imagine larger things that do sensor planning over the long term. But if this density is anything but a very simple density, this becomes a very complicated question. And so the student did something. This is Dan Hu, which is simply grab the image where there is the most black, variance. Meaning, this flag is constantly being changed, so we constantly take images there, and once in a while we take a large wide-angle shot because that has the highest information value. And then here's actually a building going up, so here we're constantly resetting those variances. So the camera spends a lot of time sampling this part of the image and trying to follow the building as it goes up, right? And that's the animation of the large gigapixel fovea eye in the sky, which is, it's actually a very, very simple thing we did, but it shows the promise of this. In future plans, if we want to make the densities actually more informative than simply independent pixels. And there is some very interesting work in that area that we're trying to implement. But there is also some interesting research to be done about interacting with these gigapixel images, which have independently changing pieces, right? So this gigapixel panorama here has a little piece here that is constantly changing. So the system could figure that out because it has put all these images there and give you a little player interface in this part of the scene. And because this building is going up in a different part, the player would be only limited to that piece of the building here, and you can independently play these little embedded movies in the gigapixel panorama, whereas the rest of the scene is static and is not considered interesting to put interaction. And then, as I said, another interesting thing is we only put on in one sensor right now, but we'd like to put in at least 3 to see what we can do with multi-view capture over time. Okay, I'm going to stop and acknowledge especially Kevin, who did the tag localization, Grant, who did the cool 4D demo and the 2 CVPR papers, and Dan, who implemented all the gigapixel stuff. So I'm going to leave it there. Thank you.
In your big panoramas, you want to factor out things that are periodic with the time of day. I would guess like shadows and maybe even traffic and what's happening in the sky. So I wonder if you've thought all about how you can correlate, say, pixel brightness with just time of day. You might find some periodic correlations.
Right. Yeah, absolutely. I mean, so that seems to be the way in which to attack shadows, right? Because shadows are not perfectly periodic, right? They change by time of year. So you're not going to totally get away from it. But you could, add a time of, do it in modulo 24 and then modulo sun time, especially if you capture this over many, many years. So I don't know how to do it, is the answer. But definitely, I think that's the right direction to think in and trying to factor that out. Yeah.
Great, thank you very much. So we have a 30-minute break. We'll start the next session exactly at 4 p.m. sharp. There should be snacks outside.